Hello ladies and gentlemen, this is my project on additively manufactured Ti-64 post-institute residual stress treatments. In the modern world of advancing sciences today, there is a need for complex metals in fields such as the biomedical field, aeronautical, aerospace field, things like that. And in these fields, the need for lightweight, the goal of these materials is to have a lightweight material with high durability. And one way to do this is through additively manufacturing, which is basically 3D printing. And with this project, it was additively manufactured metals. The way that we did it with this one was laser powder bed fusion, which is basically it lays a layer of a powder down, and then a laser goes over it to melt the powder, and then do this layer by layer. And as you can imagine, you can make a pretty complex material with this. And with one problem that arises through doing this process is something called residual stress. Residual stress is something that builds up in the metal over time as you do this, and it can weaken the overall durability of the metal, and it can cause problems for just longevity of the material. My goal of this project was to reduce residual stress while keeping the overall microstructural process, microstructural mechanics the same, and overall hardness the same as well. That was my goal. My question is, will this mid-process residual stress treatments, will it relieve the residual stress while keeping the microstructure the same? So to first begin with the materials list, we have we've got the Ti-6Al4V powder, which is 90% titanium, 6% aluminum, 4% vanadium. This powder was pre-prepared at Wright Pett Air Force Base, which is where I did this project at. And some parts of this project, I had the assistance of some doctors, and one specific doctor I would like to thank is Dr. Butler, who helped to work all of the harness things, the printing machine, and the 3D print, and the microscopes, because I have optical microscopes and EVSD maps, and I certainly can't do that on my own because I'm not a metallurgist yet. Hopefully in the future. So moving down with the materials list, we've got the laser powder bed fusion, and I've got very specific examples here, and I have it in my paper as well. Sorry that you can't see it directly. The camera quality isn't always the best. And then going down next, we have the hardness. We've got the polishing materials, which I'll go into detail in a second. And then we've got the hardness tester, and then we also have the optical microscope and the scanning electron microscope, which is all right here. And those are my materials list. And going to the procedure. So first, they prepared the powder on base, like I said, at Wright Pett Air Force Base. And then I was able to 3D print this metal, and it was about a 1x1 cube was what we went with here. And it was cut in half so that we got an XY and XZ plane. The goal of the XY and XZ plane, because as you can imagine, this is the XY, this is the XZ plane, if you can see this. The goal here is because, as you can imagine, as you're building this layer by layer, the XY might be different because you're putting powder on top of the preheated metal, like pre-melted metal, and doing this layer by layer. I thought maybe it can just reduces the overall structural integrity of the XY plane, and so I wanted to test that as well as all the XZ plane. So I was able to do that. We cut that with a water jet. Don't remember the exact name of the jet itself, but it was a water jet. And then after I printed the metal and cut it, I then polished it. And then with the polishing, how that works is first with the metal, mount the metal in epoxy resin, and basically how that works is the powder, and you put it into this chamber, and it compresses it and heats the epoxy resin to the metal at a really high temperature. And it's so that you can grip the metal as you polish the material, which I'll get into in a second. To polish the material, you hold the epoxy resin, which you just melted to the metal, and you're gonna have one surface of the metal exposed. And then there's gonna be a rotating pallet with a certain grit level on it. And we started at 640 grit, I believe, and went down to 240 grit. And how that works is with 640 grit, we went from 240 grit to 640. With 240, the surface is really rough and really textured. And how that works is you're gonna hold it there, and the circle of the plate basically holding the really rough surface is rotating at 200 revolutions a minute, and you're going to hold the material to it, and it's going to rotate it, and it's going to create crevices in one direction. You're going to rotate the metal 90 degrees, and then you're gonna go up in the grit level, and as you can imagine, you're gonna get higher. The roughness of the paper is going to get less and less, and you're going to create crevices closer and closer to the material, so that you have very fine crevices. And then to finish it off, I soaked it in a diamond finish to give it that mirror finish, which is used for hardness testing and later microscope imaging. And then after I did that, I did the microscope. I looked at the microscope, and these are the images here, which I'll get into in a second. After the imaging, I did hardness testing on the material with that one. We just according to the Vickers hardness scale, and how that works is it's basically a diamond tip. It's like a pyramid, you can imagine, and it indents the material. With this project, it was 15 grams of force, and it measured the length, width, and depth of the indent. They calculate the hardness, and I did 10 indents per sample, and then averaged it to get the data that is presented here, and that is the hardness levels of it. And yeah, the hardness testing, and that was my overall procedure here. So with this one, I had two specific material. I had 4 samples. So CO1 and CO2 so CO1 was the relieved sample, the stress relief sample, so the experimental group, and then CO2 was the as-built sample, the control group, which had no residual stress treatment done to it. And so C1 was the stress relieved, so the experimental group. CO2 was the control group. We have CO5 and CO8 here. So CO5 was another experimental group with the XY plane, and CO8 was as built with the control group as the XY plane. Not XY plane. It's just the samples, and then we cut each of them in half. And so if you can look at the table here, which I have in my paper as well for future referencing. So with the XZ plane, you can imagine as you're building up, like I didn't expect to see any change in any of these planes, but they're all relatively the same, varying from 404 to 410, which isn't very big of a difference in the Vickers hardness scale. And then you go to the XY plane, which I was very happy to see, very surprised, is that in the experimental groups, there is a much higher hardness. So if you can see this, there's a 410 in CO5 and a 401.2 and the experimental groups compared to the 370 and the 367 and the control groups. And I can hypothesize that the reason for this change in hardness was because as we're applying this the treatment, the residual stress treatment, which is basically you have the metal surface and it goes like this. It goes over the surface. This is the flat plane of the metal, like looking down on it like this. It goes over the metal like this and shocks the metal. Because in like movies and things, you see the people you see like metallurgists hammering like knives, swords, hammer, like whatever like material made of metal at a when it's like really hot, they hammer it. That's called hammer peening. What I'm doing with this is laser peening, which is getting rid of residual stress, like I said. And with the laser peening, I believe that it further connected the material to its like previous layer, making it have a hardness like value in the XY plane, which is great news, which is great for just further possibilities of the metal, like further like what it can be used for. And so yeah, this table, the way I said, this graph explains it quite nicely. So the blue is all the experimental groups, the orange is all the control groups, and so right here you can already see CO1, CO2, CO5, CO8, like it's even line. So the blue is the XZ plane right here. Sorry, the blue is the XZ plane, and then the orange is the XY plane, and CO1. So this is the experimental group here. So very little varying change compared to the control groups right here, which is this crazy difference in hardness levels, which is great. Again, like I said, I didn't expect this, but it is great because higher hardness just is better overall. Like, why would you not want a harder material? Things like that. And then moving on to the moving on to the scanning electron microscope. So the ABSD maps. It's hard to look at one without comparing them together, and I really hope you can see this. And if you can't, I'd recommend pulling up the research paper here for that, because I have the imaging there as well. So I've got the experimental group here, and I've got the control group here. And with the experimental group, so with the control group, you can see here there's a deformity in the middle. There's a lot of ununiformity, or there's anisotropy, which is just randomness, like random directions. So there's just a lot of anisotropy here compared. You can look at the stress-relieved sample, and there's reduced anisotropy and no defects in the no like deformations or defects like this white, like teal-looking blotch here, or teal, yeah, blotch here. So already great news. Your higher hardness and the maps are looking good. You can go straight over to the optical microscopes, which we've got here. Our recommend, like I said, research paper. We've got the CO8, which are right here of the optical microscopes, versus the CO5. So this is the experimental groups here, control groups here. And you can see these two deformities here, the black splotches. This is a 250 nanometer field of view, and this is a 25 nanometer field of view, so 10x. This image is of that black dot right there. Y'all look and see that if you have it pulled up. And then you can, this is the same thing for this experimental group here, 250 nanometers versus 25, which is just a zoomed in image in the middle. And so again, if you have the image pulled up, you can see immediately no deformities in the middle, which is great overall. You've got reduced anisotropy once again, which is great for the hardness values. And that is for the imaging. So just overall great news for the imaging. So just with the results, this treated sample showed significantly higher hardness, especially in the XY plane, up to 410 versus the 370 in the controls. The consistency of hardness, the hardness values in treated samples were more uniform, while control groups showed greater variation. Like I said, reduced defects, like there's no defects in the experimental groups, which is again great. There's texture improvements. So yeah, there's so many further research possibilities with this. So like in conclusion, there's increased hardness, enhanced material reliability, uniform microstructure, reduced anisotropy, manufacturing efficiency, implications for the future products. So for this, like I said, you can have more reliable like heart valves. So in the biomedical, going to that, you can have heart valves. You've got, and then you go into the automobile industry, you can do engine blocks, which are just great, like lightweight, like high durability. There's engine blocks. You've got jet engines in general, which are already starting to be produced. But with this stress relieved possibility, it is great news for like in terms of longevity of that metal. So design flexibility and long-term reliability, it's just a catalyst for future innovations in general. And yeah, so for recommendations, if I was to do this future work, I would first, so if I were to do this again, I would fine tune the laser to find the exact pattern of the, the treatment would be best for it. And with this one, I chose 16 for the pattern. Like it's going to go over this sixth, it's going to do, this is 1, it does a 16, like this is 1, so then that's 2, and so it does 16 times. I chose this because I wanted to choose a 1 in the middle. Too high would mean it might deform the metal, and it would just have too many effects on the metal, which would overall decrease the hardness and microstructure. And I wouldn't do too low or do nothing to the metal. So 16 was a nice number there. So if I would fine tune the laser to find the exact point where it would be a great pattern for that. And then if I was to do again, I'd compare it to post-process studies. Because maybe mid-process or in-situ processing isn't the best, and maybe post-process, there's a better post-process way for additive manufacturing out there, and that this isn't the best way to do it, but it's definitely one certain way. And yeah, if you have any questions, feel free to comment, and thank you so much for your time, and I should thank you judges for judging my project, and I hope you have a great rest of your day.